Hi, welcome to the screencast for 18.1. Chapter 18 starts looking at acids and bases. And acids and bases have a lot in common with the stuff we've looked at in chapter 16 and 17 as far as reaction rate and equilibrium. So starting out with the basics here, some of the characteristics for acids and bases are that acids tend to be in foods we eat. They help digest our foods, that's stomach acid. Anything that tastes sour has likely got acids in it. Bases, on the other hand, tend to be in household cleaners. They're used in antacids, which is like anti-acid for when your stomach has too much acid going on. We eat a few foods with them. They tend to taste bitter. And you can tell when you have used a base because your hand has a real slippery feel to it. And you've maybe noticed that after using some cleaning products. Every substance can be classified as either being an acid, a base, or a neutral substance. Other properties of acids and bases is that they're both good conductors of electricity, but pure water is actually a very poor conductor. Fortunately for us, or unfortunately, we rarely have 100% pure water, so tap water is not pure water and will still be a decent conductor of electricity. Acids, you could be tested by using litmus paper. Acids will turn blue litmus paper red, whereas bases will turn red litmus paper blue. Or you can use a combination paper called pH paper, and acids will turn the orangish or yellowish pH paper red, and bases will turn this pH paper a blue or a green, similar to what we saw in the launch lab. Another characteristic of acids is that they react with many metals to produce H2, hydrogen gas, or they'll react with metal carbonates to produce hydrogen gas and carbon dioxide gas. Group 1A metals tend to react with water to form a basic solution. So what makes an acid and a base a base? It's all about the hydrogen and hydroxide ions. And the hydrogen ions are also called the hydronium ions. So hydrogen ions have an H with a +1 charge, whereas hydroxide ions are an OH with a -1 charge. And these are both familiar to us from things we've done earlier this year. And if you think about it, water has one of each of these. It has an H+ with an OH-, but we condense that into H2O. So neutral solutions like water have equal numbers of each ion. If all of your water molecules broke apart into H+ and OH-, you'd have exactly the same number of each, and that's what's considered a neutral solution. Acidic solutions have more hydrogen ions than hydroxide ions, while basic solutions have more hydroxide ions than hydrogen ions. And that's what gives them these different characteristics of tasting sour or tasting bitter, but allows them both to be good conductors of electricity. The earliest model of acids and bases, and by model we just mean a way to define or understand acids and bases, is from a Swedish fellow named Arrhenius. And he said an acid donates H+ when dissolved in water, and a base donates OH- when it's in water. And a neutral substance donates neither H+ or OH-. And this model works well and explains most of the acids and bases, but not quite all of them. Ammonia, NH3, is one that actually kind of breaks this rule, or sodium carbonate. They both actually produce hydroxide ions, and neither one of them contains OH. Ammonia has H but not O, and sodium carbonate has O but not H. So something else has to be going on. So this Bronsted-Lowry model is a combination of two scientists' work. It's a different model that focuses on the hydrogen ion only, and it can account for all acids and bases. And it says that any substance classified as an acid or base in the older Arrhenius model is still an acid or a base in this model. It doesn't change anything on that, but it includes some of the things that the Arrhenius model didn't, like NH3 is a base and sodium carbonate is a base in this model. So what's different? Acids are defined as hydrogen ion donors, and bases are defined as hydrogen ion acceptors. And then they also have what are called conjugate acids and conjugate bases. And if you're taking a foreign language, you know that you conjugate verbs. Conjugate just means to transform or to become. So what becomes the acid, what becomes the base. So a conjugate acid is what forms when a base accepts a hydrogen ion, because if a base has the hydrogen ion, it's now become the acid. And then the conjugate base is what happens to the acid once it donates its hydrogen ion. It no longer has one to donate. Instead, it can accept one, so it becomes a base. And I know this is confusing, but on your left side, your reactant side, the acid has the hydrogen to donate. The base is going to accept it. So on your product side, whatever lost the hydrogen ion is now the conjugate base, or has become the base, and the base has gained the hydrogen ion, so it has become the acid. And we'll look at an example here. One analogy your book uses is it says it's similar to playing catch with the ball. You either have the ball or you're waiting to get the ball. So if you and a friend are tossing softball or whatever back and forth, whoever has the ball is the acid. Whoever's waiting for the ball is the base. When your friend throws the ball to you, you just change from being a base to being an acid. And that's where this idea of conjugate acid and conjugate base comes in. So look at my example here. HCl, you should remember, is made up of H plus and Cl minus ions. And when it's in an aqueous solution, it actually breaks into these two ions. So it is no small task for the H plus to hook up with the H2O and leave the Cl minus all by itself. So that's what we see over here is H2O with an extra hydrogen and a +1 charge, and the Cl ion left all alone. So the HCl lost its H plus, so the acid became, oops, I'm sorry, I didn't take my arrow far enough. Your acid becomes the base, and your base becomes the acid. So I've got a couple examples for you to try. So let me go to the next screen, and I'll pause it and put in my solution. And I'd suggest you go ahead and pause it and see if you can come up with it yourself. And I'll erase this mess and come up with a solution. So if we read this carefully, it says write the equation for the ionization of hydrogen fluoride in water. So that lets us know that the hydrogen fluoride is breaking apart into hydrogen ion and fluorine ion. And that means the hydrogen ion is available from the HF. And just like in the last example, it's going to go ahead and hook up with the H2O. So I'm going to have H3O plus and F minus. That means HF, hydrogen fluoride, was my acid, whereas water was my base, which you maybe noticed this in the last example. It seems a little weird to think of water as being a base. It's supposed to be neutral. But with the Arrhenius, or with the Bronsted-Lowry model, if it accepts the hydrogen ion, that makes it a base. And over here, the H3O has become the conjugate acid because it now has the hydrogen ion. And the fluorine has become the conjugate base. So the acid becomes the base becomes the acid. So I've got one more example for you to try here. So let me erase this before I advance it so it doesn't carry over to the next page. And it says write the equation for the ionization of ammonia to form an ammonium ion. So NH3 is going to become NH4. You need to figure out what the other product is and then label both reactants and products. So I'll pause and put my solution on. So once I write NH4 plus on the other side, I realize that it had to get the hydrogen from someplace, and the only place to get it from is water. And if you take a hydrogen away from water, you're left with OH minus. So that means NH3 is my base, and this time water's my acid. So now we've seen an example of water being a base, being an acid, and we also know it can be neutral if it doesn't do either, if it doesn't gain or lose a hydrogen ion when it's mixed with things. And as far as my products, I have NH4 with the plus, and as I said, the OH minus. So the NH4 is my conjugate acid, while the OH minus is my conjugate base. So hopefully this will help you as you work on the 18.1 problem set.